Awesome. Thanks, Ben. Yes, so there's been a change from the advertised content of this talk. And basically, I'm not going to be talking about a pseudo likelihood incorporating multiple levels of kinship together with kinship uncertainty. And the reason is largely that I found and read this paper by Hans Skog from 2001, which includes a lot of the same ideas and possibly done much better. So yeah, I won't be talking about that today. Sorry if you were looking forward to that, but maybe you could check out this paper if you haven't already. It's a good one. So this is work that I did for my BSc Honours dissertation last year, and my supervisors are Rachel Fuster in statistics and Emma Carroll in biology. I'm going to talk about close kin genetics, this simulation that we've done for New Zealand southern right whales, distinguishing self and parent offspring pairs, and the pseudo likelihood that we get from them, and then show some preliminary results. So the key intuition of close kin genetics is that in larger populations, you're less likely to find closely related animals. There's a good reference here from 2016, Bravington et al., close kin mark recapture. Basically, you go from observed genotypes of animals to kinships between pairs, and then you can make a pseudo likelihood for your population dynamics and demographics parameters. Specifically, the ones we're interested in are population size over time, population growth rate, and the survival probability. So this is the New Zealand southern right whale. We want to apply close kin genetics to estimate the recovery from whaling. We have some knowledge of its population and exploitation history, life history traits, and genetics. We're unsure of the effect of female breeding cycles, so females only breed every few years. And also it's a small population on the order of thousands of animals. So as Mark mentioned last night, we're not sure about variances for estimates in such small populations. So it might be a good one for simulation. So this is an estimated population and catch trajectory from Jackson et al. 2016. The blue line is the population history and the red histogram is catch. So you can see that there was serious whaling in the early 19th century that caused the population to crash from about 30,000 whales down to about 100 at the bottleneck, and it's now recovering and estimated to be about 4,000. We've got an estimated survival probability of 0.97. Animals only breed after about 8 years of age. Females have one calf at a time and breed in order of time since last breeding, about once every 3 years. And we don't know of any selectivity in male breeding. So genotypes are observations of alleles at one or more loci. We implemented 3 kinds of genotypes in our simulation, but the most important is SNPs. SNPs, you can have many loci. They're biallelic, so you have one allele from each parent. There are 2 possible alleles at each locus, and they're easy to analyze, and the technology is advancing rapidly. We've got a web app to demonstrate the simulation, so I'll show that now. So you can choose whether you'd like to simulate the whole population history or just a part of it. The whole history takes a long time, so I've just simulated the last 70 years here. So you can see that the simulated population has followed the requested population history well in this simulation. You can see the first few animals simulated here were the birth years, sex, and genotypes are all randomly initialized according to observed distributions. And of course, we don't know the parents of the first animals simulated. Here you can see the last animals simulated are all born in 2020, and now we have the IDs of their parents. We can check that the genotypes have been initialized according to the distributions that we specified. and we can check that genotypes are being inherited as they should be. So here we have one animal and its mother. So the mother's ID is 4755 here, and this is the father's ID. And you can see, for example, that the haplotype, which is always inherited from the mother, has indeed been inherited from the mother here. We have the female breeding intervals simulated. So we've got intervals that are close to the observed intervals here, and they'll depend on the particular population scenario that you simulate from. And then the male breeding intervals follow a negative binomial distribution because there's no selectivity there. So this simulation is quite detailed and realistic, and in fact we haven't been able to use all of that detail in our modeling yet, but we've got it there. So to distinguish self and parent offspring pairs, which are the ones we're using in this preliminary model, we're using plods as they're described in Hillary et al. 2018. So from the sample allele frequencies and an assumed kinship, you can find the conditional probability of a pair of genotypes given that kinship. And then you can find the pseudo likelihood ratio for any two possible kinships. And the plot I'm going to show you is for half siblings versus unrelated pairs. So we ran our simulation with genotypes of 1,000 independent SNPs, which is a compromise between computability and our expected ability to observe large numbers of SNPs. We sampled animals in multiple surveys and calculated plots for all sampled animals and looked at the density. And so this is what it looks like. You might recognize this from Mark's talk again last night. So most of the plots are in the negative values, indicating more evidence that they're unrelated than that they're half siblings. But you can see that there are a few plots in the positive values. And if you zoom in, you can see that they actually are in these distinct bumps. And because we're simulating them, we can actually tell what the true kinships are between the pairs of animals for each of these plots. And it turns out that you have self-recaptures over on the most related side of the curve, parent offspring pairs less related than self, and then half siblings and grandchild pairs, and then becoming closer and closer to unrelated pairs here. So this is a nice thing that you can see when you do a simulation. And you can also note that conventional capture-recapture only uses these self-recaptures, whereas close-kin methods has access to all these other kinds of recaptures. So that's really what it's all about, I think. So we derived a pseudo likelihood for our, I should say that there are sort of various ways of trying to distinguish, more kin pairs here, for example, half siblings and grandchild pairs, but we just use these self-recaptures and parent offspring pairs in this preliminary model. So we derived these probabilities for these self and parent offspring pairs from our parameters of interest. So here we have n sub t is the population at time t, lambda and phi are the population growth rate and survival probability, which we're assuming to be constant. So the simplest one is the self pair between two surveys at times t1 and t2 here. And you can see that it's inversely proportional to the expected population size at the time t1 of the first survey. And then, the animal has to survive from the first survey to the second survey. And then at the same time, the population is growing during that time. So you get this fraction to the power of the number of time periods between the two surveys. The parent offspring pairs are more complicated, and in particular because we don't really have any way of knowing the ages of our animals. And so we actually had to partition over all the possible ages, and which gives you a geometric series in 1 over lambda, I think. And we found these parent offspring pair probabilities within 1 survey, and also between 2 surveys within the age of maturity, which is just a slightly simpler case because it means that the parent had to be alive in the first survey. So we compared our probabilities in terms of the expected numbers of each of those kinds of pairs with the numbers of pairs in our simulations, and we think we got the expressions right. This is the negative pseudo-log likelihood surface with n held constant, so lambda on this axis and phi on this axis. And you can see the true values in blue and the minimum likelihood values in red, with the solid being the minimum, which in this case is at the true values. And I'll show some preliminary results. We were constrained by computational complexity in the simulation and in the quadratic number of pairs, and also we're having trouble with our optimization. We simulated only 10 full population histories and only resulting in 2,000 animals in 2020, which is smaller than our actual estimates. And we simulated 5 sort of final population histories with 6 surveys occurring in each one, and at 5-year intervals, sampling 10% of the population, which is about realistic sample size. So here are our estimates. We got a CV for n of 16%, of lambda of 0.63%, remembering that lambda is held constant, and for phi of 3%. So we think these results are fairly promising. We need to speed up the computing. We'd like to implement the likelihood in TMB. We'd like to estimate the parameters of the differential equation used by Jackson et al. Rather than assuming constant population growth rate. And we can do more sophisticated things to include more kinds of kinships. So that's it for me.